Hello again. In the last two videos we learned about how the governing equations for transient simulations were derived, and we learned about the various storage coefficients for the general case of a saturated aquifer and then for specific cases for a confined and unconfined aquifer. In this lecture, we are going to learn about how to set up a transient simulation, and specifically, we're going to learn about how to enter storage coefficients into ModFlow and what storage coefficients are required. We're going to learn about initial conditions for transient simulations. We're going to learn about stress periods and time steps. That's how the time domain is discretized in ModFlow. And we're going to learn about the changing head boundary package. So we're stepping away from the fundamental theory here, and we're going more into the practical applications and the steps involved in setting up a transient model. So this is the governing equation used by ModFlow as published in the ModFlow reference manual. And on the right-hand side, we see the specific storage term. So ModFlow, or how does that relate to the inputs? When it comes to ModFlow, it requires either a primary storage coefficient or a primary and secondary storage coefficient. Now those are not terms we've used yet. This is terminology that's unique to ModFlow, and I'll explain in the next slide how that works. And so what combination you use depends on the layer type and which flow package you're using. So we almost always use the layer property flow package as opposed to the BCF or HUF packages. And in the LPF package, each layer is designated as a confined layer or a convertible layer. If it's a confined layer, that means that the layer starts out saturated and will stay saturated through the entire simulation. And in that case, the storage coefficient that you need to enter is the specific storage. That's the S sub S, the main one that we derived 2 videos ago in the general introduction to governing equations for transient simulations. So that's the amount of water released from a unit volume of the aquifer due to a unit decline in head. Now, if it's a convertible layer, and when do we use this? Convertible means that it may start out saturated, but could convert to partially saturated. And what I mean by that is it could be that the head in the cell drops below the top elevation of the cell. So it starts out confined, but could become unconfined. Or it could start out as unconfined. So if at any point during the simulation there's a chance that the head would be below the top elevation of the cell, you want to mark that as convertible, and convertible is the default layer type for all layers. So why would you ever switch one to confined? Well, it makes the solution go a little faster. But by default, they're convertible. Now, if it's convertible, you have to input 2 different storage coefficients, both a specific storage and a specific yield. Remember, specific yield is for an unconfined aquifer, and it's the amount of water lost from an unconfined aquifer from a unit change in head, and it represents gravity drainage as the water at the top of that column drains off. And it's some fraction of the porosity. It's much larger than the specific storage. And so if you have a convertible layer, when it's fully saturated, if the head is above the top elevation of the cell, it uses specific storage. And once it drops below the top elevation of the cell, it switches over and uses specific yield. And those are entered using arrays. You can set them up using zones, polygons in the map module in your conceptual model, or just use a constant value for the entire grid or for individual layers. So that's it. It's pretty simple. They're just those two cases you need to worry about. Okay, now I want to talk about defining initial conditions. When we talk about initial conditions, we're talking about starting heads. And for a steady state model, as we discussed before, the initial condition represents a guess at the starting heads, and for most models, it doesn't matter that much what you use as long as you start out with your cells saturated. So the default in GMS is to have the starting head be equal to the grid top elevation. And most of the time, that gives you a stable solution. However, things are not that simple for transient models. For transient models, you have to be much more deliberate and careful with your initial conditions, because with a steady state model, the starting heads is just a place for the solver to start, and it's as if you're running an infinitely long time step, and it eventually converges. But with a transient model, the initial conditions represent the state of the aquifer at the beginning of the simulation. And so you need to have starting heads that are consistent with your boundary conditions, your recharge, and your other model inputs. You cannot use arbitrary set of starting heads like you do for steady state models. And you can't interpolate your heads from observation wells. I've seen people do that to come up with their initial conditions for a transient simulation. So here's a quote I like to reference. It's from a famous textbook on groundwater modeling by Anderson and Wosner, where they describe this issue. And the idea is, your initial conditions for transient simulation should be a solution from another ModFlow model, maybe a steady state run or something, where you generate a solution and the heads are compatible with the boundary conditions and other model parameters at the beginning of your transient simulation. So let me read this. The use of model-generated head values ensures that the initial head data and the model hydrologic inputs and parameters are consistent. If the field-measured head values were used as initial conditions, the model response in the early time steps would reflect not only the model stresses under study, but also the adjustment of model head values to offset the lack of correspondence between model hydrologic inputs and parameters and the initial head values. That's a great piece of writing there. If that's still a little fuzzy for you, let's look at a graphical representation of what we're talking about. So let's suppose for a particular cell in a model, we start out with the curves show the head value at that particular point, and time is increasing as we go to the right. So these up and down variations of the head at this cell could represent how the model responds to pumping in a nearby well or changes in recharge that occur over time. Again, with a steady state, with a transient model, we are going to model how the aquifer responds to various stresses over time. And if we start out with an arbitrary starting head, maybe up here somewhere, as the model progresses, it will eventually, over time, merge down to where it should be. And when I say where it should be, this is a solution that is consistent with the boundary conditions, the sources and strengths, sinks, values, recharge, and so forth through the entire time. It will eventually merge, but if I have before running a transient solution, if I generate a steady state solution using the boundary condition values and model parameter values consistent with the time step at the very beginning of my simulation, then I will have a set of heads compatible with that, and any change in the heads from that point on are solely due to the transient stresses I'm applying. Whereas if I just pick an arbitrary starting head, then the head is going to be pulled down to where it should be, and if I start up high, it'll go down, but if I start too low, it'll merge up. But during these initial series of time steps, it's trying to calibrate itself to where it should be, and that's what it's talking about here. The model response in the early time steps would reflect not only the model stresses under study, but also the adjustment of model head values to offset the lack of correspondence between model hydrologic inputs and parameters and the initial head values. So we want to have something that is consistent with our starting values. Now let me show you another example. So this is the Dupuy solution, we call it. It's a rectangular block of soil, and we have a head boundary on the left and a head boundary on the right. And this is what a steady state solution would look like under those conditions. And let's suppose, for the sake of argument, that what we want to simulate is how this solution responds if we gradually lower the water table or the head boundary on the upstream side over time. So if we use a arbitrary flat water table initial condition, what happens is as the solution progresses over time, it matches the boundary on the left, but over on the right, it should be down here, but it's dropping over time, and it eventually gets to this point. So let me play that back. So this is where we start, and it goes down. So let's look at solving this a different way. Rather than having a flat water table, suppose that we ran a steady state simulation with the boundary condition shown on the left and the right, and that became our initial condition. Now, as the transient solution proceeds, it looks more like this. So again, over as I go, I'm just going to go up and down here, and you can see the difference. So the head value is pinned to the correct value on the right, and the transient changes are in response to the changing water level on the left. Let me go back and play the previous one. So this is the flat water table initial condition, and it looks like this. And this is the steady state initial condition, and it looks like this. So this is the correct solution. So the bottom line is your initial conditions have to be consistent with your stresses and boundary conditions at the beginning of your transient simulation. One way to do that is to take the stresses and initial and boundary conditions at the beginning of your transient simulation, run a steady state solution, and use that as your initial condition. Now, it used to be that for this to work, you had to run the steady state solution, then copy over the head values to your transient solution, to your starting heads array. But we're spoiled now. In recent versions of ModFlow, they've added an option. For your first time step, you turn on this steady state toggle, and it automatically runs a steady state solution with your boundary conditions and parameters and stresses corresponding to the beginning of your transient solution, and generates the starting heads that it then uses to continue on from time 0 throughout the remainder of your transient solution. But you need to understand why that's the case, and but fortunately it's pretty easy to do now with ModFlow. So in this dialogue, this is you'll notice the title here is stress periods. Let's talk about this in a ModFlow transient simulation. Your time domain is subdivided into a number of stress periods and time steps, and they are shown graphically at the top here. So this would be a first stress period, and this would be the second stress period. The little red hatch marks indicate the time steps. So each stress period has a length. So this first one is 50 days with 5 time steps. This next one is 200 days with 10 time steps, 150 days with 10 time steps, and so forth. So the time steps, the stress periods define the periods of time when your model inputs change. So you change your recharge, your pumping rate, whatever, at the beginning of a stress period. Or you define it stress period by stress period. And so let's look at a couple of examples here. Suppose you had a well and it's pumping at one rate, and then at some point in time you switch it to another rate. In order to capture this in a transient simulation, you would use 2 stress periods. And the pumping rate is constant over each stress period, and then within the stress period, you can have multiple time steps. The time steps are the computational intervals over which a solution is computed. So for example, in this case, when I change the pumping rate, when I increase it, that's going to generate a cone of depression at the well that develops over a period of time. I need to have multiple time steps in order to capture that reaction of the aquifer over time. And in fact, you can evenly distribute your time steps throughout a stress period, or you can bias them, as shown in that second stress period. There's going to be the biggest reaction to that change in pumping rate at the beginning of the stress period, so you can have smaller time steps at the beginning and then larger time steps at the end if you like. You don't have to do that. But again, your inputs can only change stress period by stress period level, and then within a stress period you can have as many computational time intervals as you want. So in this case, we just have one change. So few stress periods, many time steps. But let's suppose you have a river stage and it varies like this. You can't simulate this with 2 stress periods, and so in this case, you could have a whole series of smaller stress periods, and then you would have kind of a stepwise definition of this river stage changing over time. And so in this case, you may have maybe a small number of time steps. Theoretically, you only need 1 time step per stress period if you want. But in this case, you'd have a large number of stress periods. So how you distribute those stress periods and time steps depend on the nature of the thing that's changing in your inputs, and how you want to set that up and model that going forward. Now, when you're selecting time steps, you have to choose an appropriate distribution of time steps. If your time steps are too short, maybe you go with a time step of every day over a 10-year simulation or something. You're going to have an accurate solution, but you're going to have a really long simulation time and maybe a large solution to look through. However, it should be said that on your output from a transient simulation, you don't have to have it output a set of heads at every time step. You can choose exactly what interval you want your heads output. But if you make your time steps too long, you can get model error. The smaller time steps will allow you to more accurately characterize how the heads in your aquifer are changing over time. If you want to, there is actually a formula to help you determine this. The time step increment, you can estimate that by multiplying the storage coefficient times the representative cell dimension squared divided by 4 times the transmissivity. So the cell dimension would be like the smallest width in terms of the rows and the columns you'd put in there. I have never used this, but it is a theoretical basis of doing this. Typically, I just kind of look at how long my simulation is, and sometimes if it's a really long simulation, you can get away with monthly time steps all the way down. I think the smallest time steps I've used personally is days. Somewhere in that range usually works out okay. Finally, the last thing I want to cover here is the CHD package, which stands for Changing Head Package. The original method for inputting specified head boundary conditions only works for static conditions only, or steady state. So and this is what we've been using up till now as we've built models. It's a combination of the I-bound array and the starting heads array. So you mark a cell as a specified head cell with the I-bound array. Effectively, that gives it a -1, and then whatever head value is in the starting heads array becomes your specified head value. Well, the starting heads array is a steady state array. There's only one starting heads array. It doesn't change in time. So this original method, by definition, only works for steady state specified head boundary conditions. But if you want to use specified head conditions that change over time, you have to use the CHD package, which was added several years later and allows us to have transient fixed head boundary conditions. And one unique thing about the CHD package, most transient packages, you define a single value for each stress period, so it behaves kind of like a step function. So this is the case we looked at before. There's one value of, say, river stage or pumping rate or recharge, and it essentially becomes a step function. But with the CHD package, for each stress period, you can give a beginning value and an ending value, and then it varies linearly across the domain of that, the time domain of that stress period. So you can have a curve, a parameter that varies over time, as shown on the right. I kind of wish all of the stress packages had this option, but most of them use the step function method on the left, and so that's something to keep in mind. And that's something unique to the Changing Head Boundary package. Okay, that concludes this video, and now we're going to dig in our class lecture and build some transient models. And I have a video on this channel, YouTube channel, going through the steps involved in creating a transient simulation using the GMS interface and ModFlow.